Alright, in this lesson we're going to learn how to take the most basic form of functions, parent functions, and be able to move them around the graph, creating families of functions. Alright.
Kayla Mercado,
To start,
David Chavez, please report
we
to
need to
Mr.
know
Hansen with
the
your
functions that we're going to
uniform.
be using, called parent functions. And these are just functions at their most basic form. And they're what we use to create the families of functions through various graphical manipulations. Alright, and parent functions are as follows. So we got the constant function. That's the graph, and here's the line it creates. And it's just f of x or y equals c for constant. And this is our constant function. And then over here we have our linear function. Looks like that, which is f of x equals x. That's the slope, I believe. Linear. Oops. Yeah. Alright, and then we have the absolute value, which just makes a v. We'll just leave the v, which is f of x equals the absolute value of x. And next you got the quadratic function, just on quad for the sake of time, which is f of x equals x squared. And over here we have the square root function, which will look like that. And it's obviously the square root of x. And then over here the cubic function, which will look something like that, which is f of x, oops, sorry, f of x is x cubed. Alright, down here a little bit. Then we got, this is the cube root, which is of course f of x equals the cube root of x, and this is going to look something like that. And then two more, we got the rational, which looks something like that, which is f of x equals 1 over x. And the last one, greatest integer, which will look like steps on a stair, something like that. And then it goes this way as well. And that looks like this. Here's the parent function for that. And these are all just the parent functions, the functions at their most basic form that we're going to be using to make the families of functions. Alright, now using these parent functions we can make the families of functions using universal patterns. So if they're, for instance, we'll just make a graph right here. So if there is a negative sign in front of the function, we'll use a linear function. No, I'm sorry. We'll use a quadratic function. Here's the point we're going to be manipulating. So if there's a negative, it's going to be reflected over the x-axis here. And if there's a number in front, right here, in front of the actual function inside, that dictates the rate of increase, I guess you can say. So this would be a little wider. And then x minus 4, we'll say. And in families of functions, if there's a minus 4 inside here, that means you move it to the right, and then plus 4 is to the left. So you're going to move this point over this way, so it's going to look like something like that. And then do squared because it's a quadratic function, and then plus 2 we'll say. And anything out here, plus 2, you're going to move it up 2 points. So 1, 2, it's going to be up here. And then the opposite occurs also if it's minus 2, it's going to move down as well. Alright, so this is what our new function is going to look like down here. This is what that equals. Say it's a function f of x. Alright, so using these parameters, we can handle and create families of functions, but it's also important to note that while graphing any function, you can alternatively plug in random x values to solve for the equation, just using an x and y table. But I'd only use this method if the problem's too difficult or if you forget one of the graphical manipulations. So for now, we'll just use the families of functions. So we'll go over a few practice problems. So problem 1, we're going to want to graph the function y is greater than the negative absolute value of x minus 4 plus 2. We're going to try and graph that function. And to do this, we take our typical absolute value function. Here's the point we're going to be manipulating. And we see up here, it's negative, so it's going to be, it's going to be reflected over the x-axis because of this negative sign up here. So that's our first step. Our second step is to move it right 4 units. So it's going to be 1, 2, 3, 4. Here's our new point. It's going to look like this, but over here. And then up 2, because it's plus 2. So 1, 2 up here. So our new function, this function up here, is going to look like that. Now because this function is greater than y, or y is greater than this function, we're going to shade on the outside like so, because any point on the inside will be less than 1. So you're going to shade on the outside. All right, there's our first practice problem. And again, you can also solve this by putting in values for x on a table. All right, for our second problem, we're going to give me a moment. Second problem, we're going to observe and graph what would happen to the function f of x equals x minus 2 squared. So it's a quadratic function because that's squared minus 3. We're going to see what happens to this if we turn it into an absolute value function, like so. And to do this, it's going to be, for this problem, the transformation reflects any portion of the graph that is below the x-axis. So it's above the x-axis. To show you what I mean, that's minus 2, so it's going to be over to the right 2 units. It's quadratic, and it's going to be down 3 as well. It's going to be down here. And so it's going to look something like that. But making it an absolute value function is going to move anything below the x-axis above the x-axis. So it's going to look something like this, because it's reflecting this portion above the x-axis because it's an absolute value quadratic function. So that's what that graph is going to look like. All right. For our third and final problem, it's kind of a real-world example of the use of families of functions. And you're given the task to record the arc of a ball thrown through the air using a time-lapse camera. And your job is to write an equation representing the ball's parabola. And the initial height of the throw was 15 feet. So the data you recorded for this, time in seconds, at second 0, 1, 2, 3, 4. So the whole thing just took 4 seconds. And then you're going to record the height in feet over here. So at 0 seconds it was 15 because I said the initial height was 15. At 2 seconds the ball was at 39 feet in the air. Or 1 second, 39 feet in the air. At 2 seconds, the ball was at 47 feet in the air. At 3, it went back down to 39, and then at 4, back down to 15 where it started. All right, so using this graph, the first step to graphing this family of function is to draw and graph the parabola that this forms using these points. So, a little rough sketch of this, starting at 15. There's the curve of the ball. So it starts at 0, 15. And then it goes on to 139, so around here. This is just a rough sketch. And then at 3 seconds, or pardon me, 2 seconds, it's up here at 47 feet. This is our time, by the way, and this is our height. At 3 seconds, it was back down to 39, and at 4, right back down to 15. So here is our quadratic function that the ball created. So we're going to have to graph this. Alright, now once you have the graph, you should see right away that it's reflected of the x-axis. So you put a negative sign in front of our eventual equation. Because the original quadratic would look something like this. So it's been reflected. So you put the negative down here in our equation. And then, so since we don't know the rate of increase, we're going to just put c as our variable there. And then you see, you can also see that the graph has been translated to the points 242. So it's been moved to 242. So on the inside here, it's going to be x minus 2, because it's been moved right 2 units. And then we're going to add 47. Did I say 42? I might have. 47 plus 47, because it's gone up 47 points in height. So here's our equation thus far. And we just need to find c, which is how skinny or fat the graph is. So to find c, we're going to compare the points created by that quadratic function, and then compare those to a normal quadratic function. So a normal one, -2, -1, 0, 1, 2. This is your typical quadratic function. This is the parent function table. So it's going to be 4, 1, 0, 1, 4. Because you plug in x for 2, so 2 times 2 is 4, and so on. So we're going to compare these to our original table of the ball, which looks like this. It was 0, 1, 2, 3, 4, and then 15, 15, 39, 39, and 47. All right, and what I mean by compare is, if we look here, you see it's -3, then another -3, or excuse me, -1. Jeez, -1, and then -1 and -3. You see it's jumping down. So over here, it's 24, 8, difference between 24, 8, 8, and then 24 again. So our c value is going to be the ratio between this and this. And 24 divided by 3 is 8, and 8 divided by 1 is 8. So you have a ratio of 1 to 8 increase difference. So that's our c value. 8 is our c value. So our final equation for this problem is f of x equals -8, because it was reflected over the x-axis, and then just the rest, x minus 2 squared plus 47. Alright, and that's the answer for that quadratic function. That's the equation. Alright, well in this lesson we learned how to use parent functions and various graphical techniques to create families of functions. And your homework is to like and subscribe, leave a comment, and buy my merch. The link is in the description below. And remember, math, not meth.
Did you just hawk your crap on my YouTube channel?
That's right.